Hi guys, Sauce here. This is the first lesson of a series in using an integral to calculate volume. This first video lesson will introduce the concept of using an integral to calculate a volume. And we're going to start from the very beginning with a line. What do we know about a line? It's one-dimensional, it has a length. We're going to label the length of this line R. Let's imagine taking this line and rotating it. If we rotate the line around one of its points, we'll get a familiar shape. Rotating the line, sweeping it around, creates a circle on the edge, but the entire line and the whole length of the line is sweeping out the middle as well. We call this a disk, a filled-in circle. The disk is two-dimensional and it has an area. I could write an expression for the area of this circle. The disk is pi times r squared. I capitalized R here, so I should keep the symbol the same and change that to a capital R. Pi r squared is the area of this disk. We could take this further. Next thing I'm going to do is I'm going to draw this disk as if we were looking at it kind of from the side. I'm going to change this presentation and draw it like this. Imagine looking at this disk from a perspective. I've got a model of a disk here. Could use a coin. This is a felt pad. So this felt pad has thickness. But if it was just a model of a two-dimensional disk, then we'd be paying attention to the surface as a two-dimensional surface. This drawing here is an attempt to visualize the disk from a perspective or an angle. And the reason why I do that is because I want this drawing here to represent what's going to happen if I was to start stacking disks of a congruent disks of the same area and same radius and size on top of each other. Now we are familiar with doing that in the real world. If I set this disk down on the paper here, and I take another one of the same size and area, I could start stacking it. And these disks I could stack more. And when I do, I create a stack of disks. And these disks have a height. They're really small cylinders. And when I stack them up, I create a cylinder that has a much higher height, a longer dimension here. So on my paper, I'm going to represent stacking disks. I could keep doing it. And eventually, I could use many disks or an infinite number of infinitely thin disks and stack them up to create a three-dimensional solid, which we call a cylinder. So if the area of the disks are stacked up to create a three-dimensional solid or cylindrical shape, that cylinder is going to have a volume. We know from geometry that the volume of a cylinder, V, is equal to the base, which is a disk. Its area is pi r squared, and then we multiply by the height of the cylinder. Height of this cylinder would be the measure of this line, and the radius, again, is the radius of a circular disk or base. But what does that have to do with the expression pi r squared and the concept of stacking an infinite number of infinitely thin disks to create this volume? Well, we're familiar with doing that in 2 dimensions when we learned how to approximate the area under a curve by first estimating it with rectangles that had thickness, and then extending that concept to find the exact area by adding up an infinite number of infinitely thin rectangles. An infinitely thin rectangle can be represented by a line. We integrated the function values, or we summed up all of the measures of those infinitely thin lines to create the 2-dimensional area under the curve. The same thing is happening here. We're going to want to do the same thing, except that what we're going to add together is an infinite number of 2-dimensional areas. And what we're going to get as a sum is the 3-dimensional volume. So just like area under the curve, when we integrated function values, we got an area. What are we going to do with this to produce a volume? We're going to integrate the areas of these circles to get a volume. Now we can test that this is working by assigning some measures to the volume and the radius, or the height and the radius of the cylinder, and we can calculate the volume with a formula that we're familiar with, and now the integral that should be the same. So let's say that we have constructed a cylinder that has a height of 3 and whose base has a radius of 2. From the geometric volume equation, that's going to be pi times the radius of 2 squared times the height of 3. Finishing the math, pi times 2 squared is pi times 4, then times 3, and that gives us 12 pi. Let's think of it as an integral. We are going to find this volume by integrating circles, or the areas of a circle that has a radius of 2 with respects to x. But where does the height come into this concept? The height is going to be the bounds of integration. If we put the first circle on top of a desk and it's infinitely thin, we would say it has no height. But if we start stacking circles on top of that first one, then we're going to make the height that comes about when we stack them up. So if we start at the desk and say that's 0, and the stack of which we're adding together to create or to make gets up to 3, that's the same as the bounds of integration in the setup of the integral. We're going to start with a lower bound of 0, like starting our stack on the desk, and we're going to build up to a height of 3. Let's integrate. This integral, I'm going to put a line here to separate my math. The integrand of this integral is a constant. I can see that if I square 2 and get 4 pi, because pi is not a variable, is a constant. So the integral of a constant is the constant times the variable that we're integrating with respects to. In this case, let's call it x. We're going to apply the bounds with the fundamental theorem of calculus, now that we have the antiderivative, or the antiderivative 4 pi times x on the bounds from 0 to 3. And we know how to process this. We put 3 in, which is the upper bound for our variable, and we get 4 pi times 3, minus putting the lower bound into the antiderivative at its variable, or 4 pi times 0. This first term is 3 times 4 times pi, or 12 pi. This second term that we're subtracting is 4 times pi times 0, which is 0. And we could ignore subtracting 0 and get 12 pi, which is what we should expect. So in review, we calculated a volume by adding up areas. And in this case, the areas were disks. So the solid that was created was a cylinder, and we confirmed that we could add up the disks to calculate the same volume that we knew how to do geometrically.